그 칠판에 그거를 해야 돼요. PPT로 해야 돼요.
Sorry. Yes, right. Since I started right. What? Yes. So the entire we're going to have a 6 presentation. Each of them roughly 20 to 25 minutes. It's going to be add up to roughly 3 hours. Okay, so that's the plan. And I will ask questions. People will ask questions, so be prepared. And yes, it can be a board talk or presentation slide. Either is fine. Clarity is the key. Okay, so don't just throw out a chain of jargons. That doesn't help at all. Okay, let us know the actual information you have understood. Okay, any other question before we continue? Okay, good. So let's finish up the discussion of path integral today. And from Thursday, we will start talking about renormalization. But today, I will already start mentioning some bits of renormalization already. Okay, but without actually, computing anything concretely. But again, let's finish up the discussion of path integral. So last time we started talking about the fermionic path integral, right? And so we sort of built up the rules. So for instance, given the Grassmannian parameter or variable theta, and then if I look at the most general, like for instance, in this case, single parameter case, this is it, and then we know this. Okay, so because d theta with the c number is 0, d theta with the theta is equal to 1. And then obviously one can think about more general case, and then we mentioned, for instance, let's just look at the concretely, d theta, d theta 2, and then if I want to compute the theta 1 times theta 2. And one thing that you already noticed is in order to render non-zero answer, the integrand must have the same number and same kind of thetas as appearing in the measure. Right? That's the only way you can get the non-trivial answer. And then since this is Grassmannian or Grassmann variable, I can first rewrite it as minus d theta 1, d theta 2, theta 2, theta 1. Now this gives me 1, and then if I after that gives me 1. So that gives me 2 cases. Okay, so basically this captures, if you like, the essence of Grassmannian integral.
No, Professor.
Yes.
The first integral should be A.
Very good. I think I agree with you. There we go. So we're on the same page. Okay. I also mentioned that the Grassmannian integral can be thought, for instance, this can be thought of as also doing a derivative in the same order as a measure. And we talked about how to do their derivative too, which is basically the same thing as the C number. So good. So once we understand the basic rules of the fermionic path, in this case just the Grassmann integral and derivative, let's look at an example that mimics Gaussian integral as you saw in a bosonic case. So for instance, let's write down the formula. So bosonic Gaussian integral. That looks like a pp, it's the minus half a p squared. So that gave me what, 2 pi over a. Right? So we looked at that. And then one can look at the matrix version of that. So just to set up the notation, let's just write that down. Let's just write it as P1 dot Pn. Then we can have like matrix of this sort, and then this result by diagonalizing this matrix. Now this is n by n matrix. We talked about this, and then this 2 pi to the n is determinant of this matrix. So we talked about this was already true. Now, what about the fermionic, in this case, Gaussian integral? What is that? So first, let's look at the dumbest and simplest possible thing first. So let's look at d theta 1, d theta 2, and then let me write it as theta 1, a 1, 2, theta 2. Okay, so that looks like a Gaussian integral. One thing that I should say, I should have mentioned is that this exponential function of two Gaussian variable is defined only through its scalar expansion. So there's no intrinsic meaning of this. That's what I'm saying. Okay, this is only defined through its scalar expansion. Let's do it. So 1 minus, good, and theta 1, a1, 2, theta 2. That's it, right? Because if you go of higher order, you start seeing theta 1 squared, theta 2 squared, that's all 0. So this is maximal thing you can have here. What I'm saying is that this is just defined through this. So in other words, if I have this, I'm just gonna write as this. That's what I'm saying. So therefore now it's easy. So the first term obviously doesn't contribute at all because that gives you 0. The second one, since this A, capital A is a commuting number in this case, not even a matrix, commuting number. So what that means is that you get plus b theta 1, b theta 2, theta 2, theta 1, 1, 2. Because this is commuting, I can just move around freely without touching anything. So I just get 1, 2. Okay, so simple case, we can do it. Let's do a little bit more complicated but realistic case. Let's look at this. D theta 1 bar to D theta n bar. So there are n Grassmannian variable, and then there's another I, which I just distinguish with the bar, just to say that I have n sets of barred variable and then n sets of unbarred variable. And then suppose you want to do a look at this sort of integral. Now is ij sum over this. Okay. So once again, this thing itself is defined through its scalar expansion. So in this case, 1 minus, this will have a little bit more term before this, and then 2 factorial. Well, if you want to be technical, so there's 1 minus 1 to the square, and then theta 1, let me just simplify without putting all indices. This, and then you can put this going, right? And then eventually there will be term with minus 1 to the n, and then n factorial, and then theta, the first thing, hopefully this notation makes sense to you. Okay, so does this notation make sense to you? What I'm saying? Okay, so by which I mean here I have theta I1, AI1, J1, theta J1. So this guy represents this, and then I just did the last one, and then there's everybody between 1 and n, and then likewise IN, theta, J. Good. And you might say, do something more, think about it. If you go one more, then you start having a term with at least one of these theta bar to the squared to the 0. Okay? Good. So everybody before this term does not make any contribution. Once again, the only way you can get a non-zero answer is the integrand has exactly the same number and same kind as in the measure. So this is the term you should look at. And meaning there's algebra. Okay, and then this is determinant of the value. So, such an irresponsible way of writing that answer. So to do this, you want to check this, you want to use the definition of determinant, which is either epsilon I1 to the IN. Then if you have some matrix entry, in this case let me use I1 to n IN. And then you have to sum over all possible permutations of INs. Okay? Or there's another version. This, now it's double sum, i's, j's, I1 to the I, oops, IN, J1 to the JN, and then now I1, J1 to IN, JN. So just to see the feasibility, without tracking the minus, I mean, maximum mistake you can make is minus sign. So let's see how. So 1 over n factorial, very good, I'm happy. And then I have all combination of this A of I1, J1 to the A of IN, JN. Now, in order to really integrate this guy, so you have pairs of theta bar theta, which you have n different kinds, right? So here, you will have theta bar theta of the first kind, theta bar theta of n kind. So there's a chain of that. Because this is commuting matrix, I can just pull out and then move away. So then, first of all, you want to rearrange this guy into like theta, 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 the theta bar, theta bar, theta bar. So once we have done that, we some minus sign here. Okay? Then this will look like I1 to the IJ, IN, and J1 to the JN, right? If you just arrange things. So then this is like basically epsilon I1, IN, and then theta 1, theta n. And then likewise for the theta bar part. So basically you see appearance of epsilon, two factors of epsilon, and then 1 over n factorial combined with the rest, it is determinant. So the maximum mistake you can make is either you get the plus sign or minus sign. Okay, sort that out. Good. So that's the basics of Grassmann integral. And one thing that you see key difference between bosonic and fermionic is that in the case of a bosonic Gaussian integral, you get 1 over square root of the determinant of that thing. In the case of fermionic case, you get something that is proportional to the determinant of that thing. That's the key difference. So this obviously appears many times, many different ways. For instance, one of the tricks known as a Petit-Papa trick or Petit-Papa quantization of the Yang-Mills theory is that somewhere you get this determinant factor, and then they will rewrite this determinant in terms of like this form. Okay, so they introduce Grassmannian field called Petit-Papa cost in this way. So, for instance, that such a thing happens many different ways. Anyway, okay. So with that preparation, let's actually do realistic case. Yes.
You said the purple petal tree.
Petit-Papa, yes.
I don't know his name.
Okay.
Exactly, but I think is it very related with the proper structure of the platform? Yes.
I can answer that only if I know what you said. Hobart something.
Structure of which?
Okay, I don't know.
Oh, sorry.
But no, nothing to this. You can tell me the expression later, and then I can confirm whether it is the same trick or not. So basically, the idea of a Petit-Papa, which this is not the proper time to say that, by the way, because I have not went into anything about the non-identity theory. If you see some determinant of the matrix, right, you can rewrite or represent, if you want, that in terms of quadratic action of the Grassmannian field, meaning fermion looking object, although it's not genuinely fermion, with this kernel. Okay, and it's just a simple observation and trick, although it really automates a lot of discussion about non-identities. Was there a question somewhere? Okay.
I just wonder what is the spelling of Petit-Papa?
I'm not gonna tell you.
Okay. But I found it.
Very good. No, I'm not gonna tell you. All right, so with this preparation now, let's talk about the realistic case. So let's consider this. Oh, before that, let's finish up one more thing. Now, with the source now. So now let's introduce source. So how do we do that? Which corresponds to the case of like here, we also talked about doing the integration with this before, right? So let's also talk about doing the integration with the Gaussian, sorry, Grassmannian source here. So we're gonna do d theta 1 to d theta n. From now on, let me just simplify notation like so. But it should be understood that I'm keeping a specific order when I write down the measure, because different order will result in a different sign at the end of the day, right? But again, maximally it's just minus sign error. So here I'm just gonna write this as a notation. Okay. Normally I have to put vector arrow there. They will look horrendously ugly. Let me try like so. Okay, so but from now on, let me not even put arrow there. So on top of this, let's add a source term. So for theta bar, I'm gonna have this Grassmannian source, and then for theta, I will have that Grassmannian source. So this is the reason why I write this way, eventually because we're gonna talk about fermion field with psi and psi bar. Okay, and we know that we want to have a Lorentz invariant object appearing in the path table eventually. So we know this is the Lorentz invariant object. And then the other way is actually matrix, as we talked about, the completeness relation, remember. Okay, so this is Lorentz scalar, this is Lorentz tensor. And so I want to write everything in this contracted form. That's why I'm writing bar on bar, bar on bar that way. Okay? Although at this level, you know, this is just a variable, nothing to do with the Lorentz transformation. So we could have written whatever order you want. What I'm saying is I'm writing that way because eventually we will care about the order in writing this with further Lorentz invariants. Okay, so with that, let's just do this. Okay, so then this entire object can be rewritten as e to the minus theta bar a theta. Okay, so let's play out this. So first of all, if I write inverse, so you see, so obviously the the term without eta that give you original this term. Now the second term, so this is plus eta bar, a cancels theta, so that give you this. Okay, and then if you write down here a inverse, because I want to cancel out this a theta, so that will give you theta bar eta, it gives this. But since I added this, because there's a quadratic term on thetas, I have to compensate that, and that will be plus theta bar a inverse eta. Done. Now, in order to finish up the calculation, we note that if I had a Gaussian integral, sorry, Grassmannian integral, I can do a random change of variable by shift. But just like so Grassmannian integral is like indefinite integral. Okay. So this is similar to having an integral from minus infinity to infinity of some function x. And obviously, in this case, we know that we're going to get the same answer even if we make a change of variable. Like in other words, if we shift this. Okay, as it's indefinite integral. Why did I say that Gaussian Grassmannian integral is like indefinite integral? Because so what is this? I have an x. And then I have x plus 1, x plus 2, x plus 3, right? I'm doing integral. So x and x plus 1 are different number. But Grassmann is like, I am theta. I am theta. I'm not going to move, right? So So there is no like data plus another data. So therefore, basically, it's not like you can scan over the data direction. There's a single data. Okay. Therefore, this is like basically the same as doing this. And if you want, if this language is confusing, like I told you, just think about doing this derivative. In that case, it's so clear that if you make any shift by a C number, obviously nothing changes. So in that sense, derivative is totally clear, but that if I rephrase it in the language of integral, that means that if I have a Grassmann integral, I'm free to do any change of a variable in the form of shift by a C number. Okay? So these are literally C number shift. By C number shift, I just meant that this is nothing to do with the data. So more precisely, if I shift by something which is independent of the original integration variable, okay, nothing changes. Okay, so with this, now I can finish this calculation, and let me just write here because I want to compare it to that. So this integral have not changed because I just call this to be new variable, nothing changes. And we know that that gives me, again, determinant of that. And then I get this. Eta bar, A inverse beta. Okay? So this is very, very similar to, for instance, this case, other than the fact the prefactor is quite different. Okay, but this structure is almost the same. Bosonic case, you had a 1/2, but it's the same. Okay, so that's enough preparation. Now let's actually write down path integral for a Dirac fermion.
벡터는 지금 그라스마니안이 아니고.
It is Grassmann. Yes. Because everything appearing here should be commuting numbers. Okay, so I have a pair of thetas. And so in order for this to be a C number, it should be Grassmann.
Professor, what is the notation bar means in this context?
Two separate variables. That's all. And in this context, nothing. Basically, labeling for different variables. But like I told you, I'm gonna write down now path integral for psi this. Now, actual fermion field. And now bar means specific, has a specific meaning in terms of Lorentz transformation. Right? So let me do it. Now we're gonna write down this. So how do I think about this notation? Previously, in this notation, we had like d theta I, and then I have a product of them, and then I can go from 1 to n, for instance. So we did here discretized version of integration with some label. Now this discrete label now will be replaced by a continuum label. X. Okay, so it's like I have psi Grassmann variable at each x, but now x is continuous variable, so I'm just gonna write it as this psi of x. And then in principle, I have to talk about d of psi of x, product over all possible x. And this notation I'm just gonna use just using the same notation as in the bosonic path integral measure. I'm just gonna use the notation. Okay. Good. So then we have what? Like I v for x, psi bar. This is derived action with now I subprescription from the vacuum wave function we discussed last time. Okay, since I want to look at the what? Generative functional, which is the vacuum expectation between the vacua. So that's why I get this epsilon. And then you're going to have psi bar, and then we have Grassmannian source field, in this case source, and then beta bar and psi. So this is the object we want to compute. Yes.
한번도 지금 렉스 이게 컨텐츠 보일 때 그런 레비시타 같은 것들이 잘 정리되어 있어요.
Okay, so your question is, when I go from here to the continuous version, how do we think about this? Is that your question? So another way of thinking about it is that, so view this, so this is, first of all, this is not finite discretized matrix. This is an operator. And even for operator, so long as it is a Hermitian, which is the case, then I can diagonalize it with a real eigenvalue. So basically, I can do the field redefinition, okay, in the form of spectral unitary rotation, and then this will become a product of eigenvalue with the psi bar psi, and then the rest goes through the same way, basically. So in other words, I could have presented it not this way, but I could have, rotated it like so. U theta, for instance. This is valid even for continuous object. Okay? And then now this is my new variable. I don't know, eta xc bar xc. This is not diagonal matrix. Okay? So it's literally like now product of each diagonal entry. And then if I just expand, then it will be product of eigenvalues, which by definition is a determinant. Okay. But I'm not saying this. I'm not saying this that there is no subtlety regarding this. Obviously, you can say, oh, what if the spectrum is not discretized? It's continuous eigenvalue. What do I mean by determinant? I don't know. Some prefactor. You will see this prefactor is not important. So we know, but discretized case, we can understand that is a determinant of the matrix. And continuous case, if the spectrum is discretized, again, we might be able to understand it. If this is if this goes crazy, we go crazy here too. But again, this will eventually return into, by doing this calculation, on inessential prefactor. That we will just drop out it and get everything. Okay, so let's do this calculation. Good. We just literally use the formula that I erased. Right. So this will become determinant of A, which means that it's going to be determinant of this object. And then schematically, let me first write schematically, and then I'm going to write shortly. So here here is an A inverse matrix. Let's figure out why A equals. So here A, if you look at this, what is A? A is minus I this, right? Remember, Grassmann integral I wrote as minus, and then sandwiched between two Grassmann variable. So there's a Grassmann variable. I'm going to interpret as minus of rest, which is this. Okay. So okay, what do I mean by this expression? So that means, let me just write this as some prefactor n, which can be even ill-defined or infinite or whatever. So there's n, and then this will be integral of g for x, integral of g for y, and then eta of y, and then A inverse y minus x, and eta of s. That's what this expression means. It's product. For now, I have to do the matrix multiplication along index I and along index y, which is the same as doing integration over x and y, respectively. Okay. Now, what is this? So this, we're going to write it as I pi y over y minus x. That was, and it will turn out soon, but is actually nothing but Dirac propagator for the Brownian. So this is the answer. Again, this part is unclear how to deal with it. You're asking. But for instance, object that we are interested in, for instance, time ordered product of here, so two-point function, for instance. In terms of generating functional, we know that this is given by this, and then acting on generating functional and setting sources to be 0 and with the calculation. So first of all, what is this Z of 0, otherwise known as a vacuum-to-vacuum diffusion amplitude? Well, set the eta bar to be 0. This is M, the crazy factor. So basically, at the end of the calculation, this will just drop out because this is independent of eta and eta bar. Okay, so we don't care. Okay. So if you do it, now we can just expand this out. And if you expand it out, what is this? This is 1 plus that object, right? 1 plus that object. And then higher order automatically vanishes. Okay? So if you do this, you're going to get this calculation. Just literally this. Because you got to take a derivative with respect to eta bar once and then another time with eta. And what is this? Well, we know how to get this object. So that was defined as that was what's solving Green's function equation. This is all we already talked about a while ago. And so the quickest way to do it is just to do the Fourier transform. That's y, and then the method space object and delta function obviously can be also written as that. So if you add this guy here, you immediately find this equation, e by h minus m, this p is equal to 1. So therefore, pi of p is reciprocal of this factor. And then if you plug it back in, this is exactly I times from it works. Okay, so again, there can be some signs that you want to keep track carefully, but other than that, it's now doable. In fact, Grassmann integral conceptually somewhat exotic, but practically actually easier because this doesn't include much of term. Basically, it is a polynomial function. Okay. With that, I'm going to talk about one sort of a non-perturbative lesson we can learn about the symmetry from the perspective of a path integral known as Ward-Takahashi identity. Then that will be the end of our discussion about the path integral, and we will move on to renormalization. But in the discussion of a Ward-Takahashi identity, I will already mention something about renormalization, but without actually computing this. Okay. And broadly, I think in literature, sometimes people just call word identity. And I don't know historically what happened. But we'll see at least the example where, really the name word Takahashi identity attaches. So overall, word Takahashi identity is it's a statement of a symmetry of correlation function. You will see explicitly. Okay, so if you have a quantum field theory, and there's some symmetry, global symmetry by which I meant, of a quantum field theory, what can you say? What are the sort of conditions you can derive that correlation function has to satisfy due to the existence of global symmetry? Okay, so that's what this is. So there is a two different pictures which are basically related. The first one, let me start with the global version of the word Takahashi identity. So here we assume that there's a theory. So we assume there's a quantum field theory described by an action. So here by phi, I don't necessarily mean that this is a scalar field, but it can be any scalar, any field, like fermion, vector, whatever. Okay. So all I'm saying is that there's some quantum field described by the action. Assume that there is a global symmetry transformation such that phi transforms as phi prime. Okay, so transformation. And I mean, a clean, easy example of this sort is like phi of x goes to phi prime of x, which is like e to the I alpha phi of x. We haven't seen something like this before, right? This is an example of the U1 global transformation, global symmetry transformation. But here I'm being general. So suppose there's some transformation you can do such that both the product of the measure and the action is invariant under the transformation. So often by this equation, I mean that separately action and measure are invariant under this transformation. But mathematically, the result that we will derive only requires this product to be invariant. And we've been dealing a lot with the cases where action is invariant. So it might be a little bit new that you have to worry about this factor, that measure is invariant. And a lot of cases, this is true. But there's also a lot of interesting, important cases where this is not true. And when measure, once again, let me stress that by this equation, I mean, this is all possible field, not just a scalar. Sometimes this transform measure is not invariant under the global transformation, especially for fermion field, although that's not the only case. In that case, we say that there's a anomaly of the global symmetry. So in other words, symmetry that you see from the action is actually violated because measure is not invariant. And then we will have a presentation of anomaly as final presentation. So anyway, here I'm just mentioning. Okay, now suppose I want to look at the correlation function of the operator. So let me construct an operator O, which is again constructed out of path integrated field phi of x. Okay, so then let's look at the correlation function. So I want to look at the time ordered correlation function of these operators. I mean, I can talk about many different operators in principle. So my expression should be taken as very, very general. So now, you know that this is proportional. I'm saying proportional because I'm not going to write down 1 over z of 0. So that is path integral over dynamic of field phi of x. And then insertion of a classical function corresponding to these operators, which are using the same notation. And then actually. Okay, so this is not the best. Okay, so that's the object. Yeah.
That the free vacuum or interactive.
Good, good. So here, since I'm considering general field theory, let's put this. Thanks. Okay. Now, in the first step, I'm going to do a change of variable. Change of integration variable. But in the form of this global symmetry transformation. Okay, so I am making change of variable using the form of global symmetry transformation. So define prime. Let me simplify the notation without by not putting all this argument of phi's. Okay, so I literally made a change of variable. So I know that it should be same as before. Since I just literally up to Jacobian. So if you want, let me assume the Jacobian or already made this statement. So I don't have to restate anything. But this times that by assumption is the same as before. So this means this is the same as, now let me write the right order before. So that stays the same. Next slide. But what is this last expression? Well, last expression is now let's put prime to x1 and prime of x2. What does that mean? So we have arrived a one of the key expressions that we want to say. So it says correlation function of an operator that you can have in the quantum field theory must be the same as the same insertions of correlated operators, but with the field transformed. Saying another way, correlation function must be invariant under the global symmetry transformation. Otherwise, it is zero. So just to illustrate this point a little bit more concretely, let's consider U1 transformation. So consider U1, just to be totally clear, and then suppose it just transforms like so. And in particular, let's say that OI, which is made of phi, carries, for instance, charge Q1. Okay? And the exact value for Qi will be determined by how this operator is constructed out of phi's. Okay, which I'm not specifying, I'm being agnostic. So if I restate this thing, what does that mean? That means the following. So if I have O1 to On, so now I'm being very schematic in terms of this notation, should be e to the I, Q1 to Qn alpha, same. So this equality holds only if, so this is true, that means that this vacuum expectation value, there's two mathematical solutions to this equation. This is zero unless, this is one possible solution, unless Q1, Qn should add up to zero. Right? So this is just the mathematical statement. Let's understand the physics out of it. What does this mean? What it means is that if you ask a question in a quantum field theory that has a global symmetry transformation, and then if you look at a correlation function of a charged operators, so you carry some non-trivial charge under global symmetry U1, and that correlation function will be identically zero. So there's a selection rule. Unless you look at the set of operator who overall is carries zero charge under global symmetry transformation. Okay, so you're only allowed to ask, therefore, global symmetry invariant insertions of local operators. Otherwise, you will get automatically 0 with the selection rule. Okay, mindful of this condition that I stated. So I'm assuming non-anomalous symmetry. Okay, so that's the global version of the Wertheimer identity. And if you have a look at this thing before, you might say that doesn't look at all like the Wertheimer identity you have seen. So let's actually go there. So let's talk about the second version. Okay, so now let's look at the local version of the statement. Yes, and there you will learn something more, actually, and that is more often used. Let's look at the local version. So if it is Lagrangian, not just action itself is invariant, and if the measure is also invariant. Okay, so what do I mean by that? So remember, invariance, recall invariance of action only requires Lagrangian shift by total derivative. We talked about this a lot last semester. So here what I'm saying is that suppose we have a global symmetry, which actually is an invariance of a Lagrangian itself, meaning there's no this total divergence theory. Okay, then you're gonna get a stronger statement. And let's consider again Lagrangian made up some general field of phi, not necessarily scalar, but everything, and then derivative of that. And then suppose I make a phi of x goes to phi of x plus some epsilon, and then some function. Okay, so now there's a transformation of the phi, and that thing is in general function of the phi and the derivative of phi. And when I say global symmetry, I mean this is constant of space and time. Okay. Now, good. So the statement was, therefore, Lagrangian is literally invariant for now. So in order to now do it, now let's ask under local version of the transformation, which means that I'm just gonna now take a epsilon being temporarily the function of a space and time. Okay, so this is a formal trick to study global symmetry. So I have not gauged. Okay, so given a global symmetry, I'm just gonna perform a symmetry transformation, but using a space-time dependent parameter temporarily. And you will see what you can learn by doing this. So if you do that, then you know that the Lagrangian now will go like original Lagrangian, and then this. And once again, we talked about this when we discussed all the symmetry aspects. So A, obviously, if this becomes space-time independent, that goes away, you recover your invariance. B, because the only now dependence on the space-time dependence of the epsilon parameter, therefore should be captured by the derivative of epsilon. So I'm just writing down here leading order in epsilon, but fully general in terms of x dependence, because I'm just going to keep every possible x dependence. And this is how we talked about. This is Noether current of the global symmetry. Yes.
Can you explain one more time about why you consider it just derivative of epsilon there,
Good.
not epsilon?
Right. Since we started out by saying that the theory has a symmetry when this is a constant,
Close.
yes. Whenever this becomes x independent, I know that my Lagrangian must be invariant. The only way this is not invariant is due to the fact that this carries x dependence, which means that it has non-trivial derivative. Okay, and then I just call whatever that multiplies that factor to be correct. Okay, good, good, good. So then let's consider so with that understanding, let's consider again a set of operators made out of this thing. And then under the transformation, this will transform as phi plus epsilon r f of r. And then I can rewrite this as original, because I'm considering infinitesimal transformation, epsilon r multiplying rest. I can define the notation like so. Okay. So now I can ask again the same question, the exact same question of what does symmetry imply on the correlation function? So that's the question that we're asking. Let's do it. So therefore, let's ask. Okay, let's look at this first. So interacting vacuum, and then let's look at a correlation function of time over correlation function of this, and this again proportional. Okay, just like before, I'm gonna make a change of variable. And so I know that it must be equal to the previous expression. I'm just writing p phi prime. Now I'm making a change of variable in the form of local form of global transformation, global symmetry transformation. Phi. So let's see. Phi. I assume that the manager is invariant, and that action shaped by this. That's this. And on the other hand, this guy shaped as this plus epsilon. Oh, let me actually just put I. This is more conventional. For instance, if you imagine, phi goes into the I alpha phi, delta phi is like I times whatever changes. So let me just introduce I, so that I don't want to, carry around a lot of i's there. So that means this is I times epsilon r variation of O, under the global symmetry transformation. Okay, so now let's collect term by term. So first of all, into the s. So that's the term. 1 plus, so let me explain this. B for x. Okay, so to leading or in epsilon, let me just truncate there. And then I have the same. Okay, so now we will get something. Since this thing has to be the same as this, which already captured by the leading order in epsilon, meaning epsilon to the zeroth order epsilon factor, already saturate this, the rest must add up to 0. So that gives me I, so I'm just collecting here, integral over x. And remember, this is an operator now, meaning, okay, this is sorry, let me say it again. This is a classical function, but when I rewrite this in terms of, let me just write, let me just do it. X r, and then we're gonna have that integral of e to the s, and then j mu O. That's the first term. So I just pick up the first order in epsilon, zeroth order in epsilon. And then with the base vector, so that's this term. Should be minus, so minus here, plus I. Epsilon, suppose I inserted an operator at y, just to be clear. Okay, suppose I inserted an operator at y, like so. So then this everybody is at y. So this is everybody is at y, just to be clear. So then this expression, ER is at y, and then that integral is like this, and then variation of O made out of phi at y. Good. So to finish up, let me do the integration by part here. Well, I could have done it here. So probably the better way is that suppose I do it this integration by part, epsilon of x, okay, of x. So suppose I have done that and then collect it again. So that means what I get, therefore, is so I cancels, and then this I can rewrite as integral over d for x delta h minus y epsilon over x. So that I can collect epsilon term together. So then you should arrive at basically everything you have is the following. First of all, left-hand side is derivative. And now this is vacuum expectation value of time order correlation function of at x. Remember this is an x, and then operator at y. That's the left-hand side. Okay, so this minus goes away because of integration by part, I cancel. Right-hand side, on the other hand, is delta for x minus y, and this is vacuum expectation value of time order correlation function of a variation of that operator under the symmetry transformation. Okay, so this is the result. And now we're going to interpret what's the meaning of this expression. Okay, it's the exact same thing. Change the variable, and then just collect the rest to set to 0. That's all I have done. Nothing there. Yeah. Yes.
그 가장 부분 중에 첫 번째 줄이랑 두 번째 줄이 맞추니까
Sorry. You're asking this is equal to that?
yes.
Yes. The first line should be same as the second line. This. And then this I just rewrote in terms of this.
왜 같아요?
Because when I go from here to there, I literally made a change of variable, right? So whatever I got here should match with this. But if you look at this, already zeroth order in epsilon saturate this, which means that first order in epsilon or even higher order in epsilon, they all have to add up to 0. Okay, so I just read out. So first order in epsilon, zeroth order in epsilon, that's the top line. Then zeroth order in epsilon and first order in epsilon, that's the bottom line. So they have to add up to 0. Okay, good. So this is the key expression. Let's understand the meaning of this. And then we're going to generalize.
Does it only hold for the symmetry which don't change the Lagrange?
Yes. Yes.
오늘 이거 그 라그랑지안 업트 토탈 데리프트 변형시키는 시메트리에 대해서 주목하지 않나요?
Okay. So technically, I assume that let me consider the case where Lagrangian is invariant to simplify my mind. Okay. However, if you have a shift by total divergence under the symmetry, you just need to modify what you mean by terms. Then the rest should go. If that was your question. Okay, so now let's understand the meaning of this. Classical theorem regarding symmetry tells you that if you have a unbroken continuous global symmetry, there should be a conjunct curve. So this is Noether's theorem. This is quantum version of that, but realized at the level of correlation function. So suppose X, where you inserted a current operator, never coincide with the location of a operator inserted for other stuff. Okay, which means that this is over 0. Then this equation just tells you that quantum mechanically divergence of expectation by a current is 0. Okay, so you're happy to see this indeed, but quantum version. However, quantum version tells you a little bit more than that. When X coincides with Y, in other words, you have this current, and then when this is separated away from the location of charged operator over Y, nothing happens. You just get the fact that there's a conservation. But when this crosses that location of charged operator insertion point, then it says whenever that happens, all of a sudden this operator goes through global symmetry transformation, meaning now J now performs global symmetry transformation on this charged operator O. Okay, so that's what this statement. Okay, now we should write down a generalized version of that statement, which let me do, and then we will consider a specific example where this name actually directly applies, meaning the example of QE.
Is it possible to derive what Takahashi identity from the canonical quantization?
I think so. Although you're not going to get like this non-perturbative version probably. You have to work it out order by order. So, okay. In fact, it may be best. First, I state the word Takahashi identity for QED, and then I can say perturbative version of that statement, which I guess historically people computed and checked. But here we are seeing, if you like, non-perturbative version of statement. But here I'm not assuming what order in perturbation theory, right? This is the exact expression. So I believe that yes, canonical quantization you should be able to derive it, but presumably you might see a perturbative aspect of it. Okay, so then that equation, I can write a general version of that. So what will be the general version of that? So let's look at a symmetry associated current, J mu, and suppose there's some index R if it is a non-abelian number. And then suppose you have a product of insertion of multiple operators. Okay, so now you just have a chain of local operators. Each of these carries non-trivial charge under the global symmetry that we are talking about here. Okay. Then this is equal to sum of. So whenever the location of a current coincide, let me actually write a y of I just so that it's clearly distinguished. Whenever I coincide with that, what I have to do is I have to perform a transformation of that object, so I, then leaving the rest in. Okay. Yes.
I'm a little bit confused with that. The derivative of mu in the left-hand side
Yes.
is up to x.
Yes, this is with respect to x. Yes. Okay, good. So that is the word Takahashi identity. So it's really about the global symmetry. Now you might say, oh, we have seen the case where like, there's a word identity for gauge invariance. What's the contact? Well, before we talk about the contact, now let's actually apply this word Takahashi identity to QED. Since we learned the QED. So let's consider the example of QED. And we have to talk about the symmetries. So QED action, we consider photon I G and slash mass this. Okay, so let's look at the QED. Plus. So now, this thing has several invariants that we have to talk about. So first, there is a obviously U1 ENN transformation under which, so for instance, psi goes either to I, G, lambda psi, and psi bar goes either to minus G, where G is gauge coupling. This is principal space and dependent. Psi bar, and then photon goes to, this is up to psi. Again, this is up to psi. We can check whether this should be plus or minus. This is minus, probably that's plus. Okay. Yeah. So this is not a Glover symmetry. Now, so this is gauge invariance. Let's make sure. Now let's talk about Glover symmetry. So there's two different kind of Glover symmetry in QED. One is called U1B, where V here stands for vector light. Vector light. Okay, so under this is not Glover symmetry. Psi goes to e to the plus I alpha, which is a constant, since I'm talking about Glover symmetry. Psi bar goes to e to the minus I alpha psi, or but A stays the same. So I literally make a Glover symmetry transformation. There's another one, let me finish up, called U1A. A stands for your axial. And in this case, it goes like gamma phi alpha psi. You can also read about that over here. And A stays the same. So what is actually the difference here? I wrote down three different U1 that looks pretty much related and similar. So let's actually decipher. So in order to do that, let's write a Dirac fermion for electron as this electron, left-hand electron has right-hand electron dagger. That's the Dirac spinner. So then in this language, under U1B, left-hand guy goes like this. The right-hand guy transform oppositely. Under the U1 axial, they transform the same. That's what this gamma phi controls. So if you want, for U1 vector, there's an identity sitting there. Therefore, U1 axial instead of gamma phi sits there. Okay, so that's the difference. Just like 1 versus gamma phi, you have the same because you have same. Oh, can I look at the Yukawa looking direction with the 1 here versus gamma phi sits there. Okay, so basically here you have 1 for the identity as a generator, the other for the gamma phi sitting there. Now, why there's name like vector versus axial? It's, I don't know who first called that way. So vector-like, whenever you have a matter field carrying charge U1, you have the same amount of matter carrying opposite charge. You call that it's a vector-like. And because in that case, such a symmetry, without showing how yet, does not suffer from a anomaly. So in this case, the measure will be, in fact, invariant. Okay? So without showing explicitly, let me just state that whenever the symmetry has the same amount of, positive charge and negative charge, then whose measure is invariant. So under that symmetric transformation, measure is invariant. Axial, when there's a imbalance between positive versus negative charge. In this case, this is maximally imbalanced because everybody carries positive charge. There's no negative charge. Then, in this case, measure of the path integral is not invariant. And when we derive Ward-Takahashi identity, we assume this so far. Okay, so therefore, we're going to explore Ward-Takahashi identity for this U1B symmetry for now, for QED. You might say, oh, is there a version of this identity including this non-invariance of the measure, meaning including the fact that there's an anomaly? It's called anomalous word identity. So there's extra term appearing on the right hand side, which captures anomaly. But for now, we're going to explore this. Okay, so let's do this. Any questions? Is that clear what I'm doing? So I derive general statement, and then I just look at particular theory called QED. And then I introduce you there are two different kinds of symmetry. One of the symmetry suits to this discussion since measure is invariant, the other is not. Even though there's a modified version of it, for now let's forget about this. Let's just focus on this. That's what I'm saying. So, so then we can write down Ward-Takahashi identity for this. So in order to do that, let's look at the 2-point. So we're going to look at a psi x1, psi bar x2 in QE. Okay, so that's my operator here. Okay, so that's my operator. So then Ward-Takahashi identity for this in QED is this. So derivative of x, reduce it to x, just to make this thing clear. And then we're going to have insertion of current. In this case, this is noidal current for U1B. So this, in fact, is actually psi bar, this, as you have seen. And then, again, we are doing the Ward-Takahashi identity for this correlator. So psi of x bar x2 is equal to. Good. Now, I'm going to first look at the case where x coincides with x1. That means in that case, I will pick up what? Variation of psi of x, but without doing transformation of the second vector. And then second time, I'm going to look at the case where x coincides with x2. In that case, I will have variation of psi bar. This is the Ward-Takahashi identity. It's literally applied it. Now, how does the psi bar transform? Remember, psi goes to the I alpha psi, and this. Remember, the notation for this, without including, so full variation is given by parameter times this vector. Okay? So when you see these guys sitting in this identity, you're only taking this expression without including the parameter cell. So variation of psi is therefore an I times. It's literally just a psi of x1. And the variation of psi bar, remember psi bar goes into the minus 9 alpha of psi bar. So therefore, this is minus psi bar of x. Good. 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 So then let me just use this space to finish up. The WT identity is therefore minus. So word Takaichi identity or word identity short is divergence current within certain depth operators is same as coincidence with that minus, which captures literally exactly the charge of psi bar and this. Yes.
I think there should be H coupling or the phase vector alpha in the right hand side.
No, remember, so that's what I mentioned. So O goes to O plus I times parameter times this expression. And in the word Takaichi, only that factor appears. So if you look at here, variation, so this varies 1 plus I alpha psi. So not I, not alpha, only writing down the rest. This,
The alpha terms will be cancelled out in the left and right side.
which already happened. Remember, there was epsilon r times that. So I just stripped out alpha epsilon together. Okay. So far, it's derivation. It's a dry looking object, right? Now the question is, what is the physics here? Okay, so I have 5 minutes. So let me state the meaning of this equation, and probably that will be it. So, what is this? What is this object? First of all, let me draw a diagram corresponding to the left-hand side. So basically, at x1, there's a fermion, and x2, there's a psi bar. And then at some point x, I'm inserting current. So that's what this is a three-point function telling you. So basically, non-perturbatively, I'm inserting a current, and then I'm using this notation because current can couple to field, photon field, or background gauging field. And then let me draw a block to say that this is any order in perturbation theory. And then there's a fermion field inserted at x1, meaning you can create a fermion using this. Again, you can go there because I'm looking at the connected diagram. And then similarly, you can have this. So that is the subject. And this block can include a lot of information. First of all, this particular chain, the pins, include fermion propagation, but possibly all possible diagrams, corrections that happens in perturbation theory. And this side too, there's another propagation. This block can include a lot of quantum corrections to it, not just a single propagator, but for instance, there's a propagator in perturbation theory, but you can also have dressing like so. A lot of correction can happen in principle. So this block basically represents the sum of the entire possible diagrams. So then this says, which we will make a sharper statement the next time and then start the discussion with normalization. This says that somehow information encoded here, which can be factorized into a piece of this part only, vertex piece, and then that is combined with the fermion propagators, because I'm just chopping and looking at each piece separately. That is related to certain combination of a two-point function, which is only propagator. So if you have some certain quantum corrections to the two-point function, meaning fermion propagator, according to this sort of diagram, that also tell you what kind of correction must be included in this vertex correction in order for this equality to be satisfied. In other words, there's a tight constraint relationship between the quantum corrections to the vertex, meaning photon to the fermion, and then quantum correction that can happen in the fermion propagator itself. There's a correlation. So this provides you extra structural constraint that QED has to satisfy. That is controlled by a global symmetry, not the gauging pairs in this case. Okay, so next time, since there's a gang outside, I will basically spend 10 minutes to write down the exact statement, what I mean by this statement, and then we will move on to the next slide.